Hey, how you doing? This is Mel Strong, and this lecture is on temperature inversions and air pollution. And we're going to start by looking at the structure of Earth's atmosphere. Now, we know something about this because every day we launch weather balloons up into the atmosphere to collect data. And here's an example of one of these weather balloons that this guy's holding. He's got this little box here, and that box is called the radiosonde. And it's like a little weather station in that it records temperature and humidity and wind and all this kinds of stuff, and it beams it back to Earth wirelessly. So all he does is let go of this balloon, and it goes up through the atmosphere. And as it goes up, it expands, because we said rising parcels of air always have to expand and cool. Well, eventually this will expand so much that it'll pop, and this will fall back to Earth with a little parachute. Now, there's a whole network of airports around the world that are designated spots to launch weather balloons. And we do it every 12 hours. And the reason for this is, in weather forecasting, you need to know what the conditions are up in the upper part of the atmosphere. So it turns out that Albuquerque's airport, the Sunport, is one of these airports that launches weather balloons. So about 5 or 6 in the morning and 5 or 6 in the evening, we'll launch one of these. And as it goes up into the atmosphere, it collects data. And here's an example of some data that was collected. It was an afternoon on the July 4th. And so this one probably went up at 5 in the afternoon. And here on the x-axis, that's air temperature. And the y-axis is height. So the red represents the temperature that the weather balloon sensed as it was ascending up into the atmosphere. So here at the surface, you can see before the weather balloon was let go, it was 90 degrees at the surface. And as soon as it was launched, the weather balloon noticed that the air is getting colder with height. And then it gets to about 50,000 feet, and suddenly you'll notice that it starts getting warmer with height. This inflection point right here, we talked about before when we talked about clouds and how we said that this makes a natural break between two layers in the atmosphere. This is called the tropopause, and it's a surface between all the air below, which is the troposphere, and all the air above, which is the stratosphere. Now, we didn't talk at the time why it gets warmer with height. Now, in this case, what happened is the weather balloon popped at about 100,000 feet. But if it could have kept going, it would have noticed that it continued to get warmer with height. So if you could look up in the stratosphere, what you would see is there are a small number of these molecules of what we call ozone, which are 3 oxygen molecules bonded together, O3. And ozone hangs out, there's not much of it up there, but it hangs out in the stratosphere. And if ultraviolet light comes in from the sun, and UV light is what gives you a sunburn, right? So we have UV light here at the surface, but we don't have nearly as much at the surface as we would at the top of the atmosphere. Because when the UV light comes down through this ozone, it'll strike an ozone molecule, and it'll break the ozone into 2 pieces, an O2 and an O. Now, eventually, through a number of steps, these 2 pieces will come back together and make a new ozone. But when it breaks it apart, 2 things happen. For one, the UV is blocked. It doesn't reach the surface of the Earth. That's good news for us. And number 2, it releases a little bit of heat. So all of these ozone molecules floating around up in the stratosphere are getting whacked with UV radiation all the time, and as a result, it's adding warmth to the stratosphere, which is why the stratosphere actually gets warmer with height. Now, the amount of UV that comes in from the upper atmosphere is so great that we wouldn't actually be able to exist on the surface if it wasn't for the ozone layer. There's so much radiation coming from the sun, it would essentially sterilize the planet. So the amount of UV that gives us sunburns is just a tiny, tiny percent of the amount of UV that would normally hit the surface if it wasn't for this ozone layer. So this ozone layer is super beneficial to not just humans, but to all life on Earth, at least everything on the land. But it's actually been declining over the past several decades. So here we have a couple images of the ozone in the southern hemisphere. And we're looking at colors that represent how much ozone is in the stratosphere. So the blue represents very little ozone, whereas the greens and yellows, that's more ozone. That's the South Pole, and you can kind of make out Antarctica down there. So we've got two images. one in 1979, one in 2012, and you can see how much more that blue is in the 2012 image. This is what we refer to as the ozone hole. Is this area kind of centered in the southern hemisphere where UV radiation can go right through that and strike the surface below because there's very little ozone here. Now, there's not a lot of people living in Antarctica, so it hasn't been a huge hazard for human health, but this was discovered in the 1980s, and there was a big worry in that this ozone hole was going to continue to grow because they could see it growing, and there was a fear that it would actually engulf the whole planet. And if it did, if we lost the ozone layer, we couldn't survive on land. So it was a pretty big deal. So scientists started looking at this in the 1970s, and they realized that there was this family of molecules that we were manufacturing called chlorofluorocarbons, or CFCs. And they get their name because they have at least one atom of chlorine, one atom of fluorine, and one atom of carbon in their molecular structure. So here's a simple one called Freon 11. And Freon 11 is a type of refrigerant. It's supposed to be inside the guts of a refrigerator or air conditioner. And as long as it's in there, it's safe. But if it ever gets out and it gets into the atmosphere, and if it makes its way up to the stratosphere, a CFC molecule will attach itself to an ozone, it'll break it apart, and then those two parts can't actually get back together like they could if they were broken apart by UV. A single CFC molecule can destroy thousands of ozone molecules. And back in the day, they used CFCs for all kinds of things. So they were a popular propellant in aerosol cans. So if you bought anything in a spray can back in the 70s, it had CFCs as a propellant. We used it as refrigerants in air conditioners. It made very nice cleaning solvents. So it was a very useful family of chemicals that were being made. Well, by the mid-1980s, it was recognized that the ozone layer was thinning, and there was a formation of this ozone hole over Antarctica. So people started to panic because they realized this was a super bad thing to happen. And in 1987, a bunch of countries got together and formed what's called the Montreal Protocol. And it's like a treaty among nations. And the agreement was, everybody, we need to stop manufacturing CFCs. And the rich countries agreed to go first and discontinued CFCs, and then poorer countries would discontinue it later on. Well, as they watched the ozone hole grow and grow in the 80s and the 90s, they got back together in the 90s a couple more times and signed a couple new treaties to kind of speed this whole process up. By 2006, the ozone hole was the largest it had ever been. And by 2015, finally, all of the countries were in on the, ending the production of CFCs. So it took 30 years from the time that they discovered this to when finally everybody stopped making CFCs. Now, just because they stopped making them doesn't mean the problem's over, because a lot of the CFCs in the atmosphere, they'll last hundreds or thousands of years. And a lot of them haven't even gotten up to the stratosphere yet. But after years of decline, and this is how much ozone is in that layer of the atmosphere. So in the 50s and 60s, this is kind of how much ozone should be up there. And we see the decline start in the 70s and the 80s. And right in here is kind of where people were panicking and starting those treaties. We see it looks like it kind of bottomed out here in the mid-90s to 2000. Technically right there, that's where it was the biggest. The ozone hole is the biggest in 2006. But what we see is that very slowly in the last few years, the ozone is starting to come back. Now it's going to take decades, maybe 100 years or more, for the ozone layer to come back to the amounts that it was previously. But because there were this protocol, because there were these treaties, because the countries came together and agreed this is a worldwide environmental problem, and they agreed to sign the treaty and they agreed to stick with it, the ozone hole is actually a problem that we as humans have solved. I mean, it hasn't been fixed yet, but it's on its way to recovery. And this is a model that we're going to talk about when we talk about air pollution and later greenhouse gases, is can we get all the countries together to agree to clean up the air and to clean up problems that affect everybody on the planet and not just the country that's making the chemicals. So we're going to return to examining these two layers. And so far what we've said is that the troposphere is characterized by the fact that it gets cooler with height, whereas the stratosphere gets warmer with height. We also said that the stratosphere has ozone and the troposphere does not. Now, there's also several other very important differences. Notice what happens with dew point. So dew point at the surface was about 40 degrees, and then you see it goes down, 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 down. And by the time you get to the stratosphere, the dew point's like minus 100. So that's super, super dry air. Most of the moisture in the atmosphere is down near the surface, okay? And in fact, if we look at what's happening in the troposphere itself, it has almost anything you'd be interested in regarding weather. All the clouds are in the troposphere. 99% of all the water vapor is in the troposphere. Everything you think of as weather is happening in the troposphere. And in fact, 75% of all the air molecules in the entire atmosphere are in the troposphere. Now, what's the stratosphere like? Well, some people that have more expendable than income than I do get cell phones and buy weather balloons, because anybody can buy a weather balloon, and they tie their cell phone to a weather balloon and they launch it. And I guess they have some app that just automatically takes pictures, and then they use like their Find Your Phone feature to find the phone when it lands somewhere. And so here's a picture taken at 100,000 feet. This is right here where our weather balloon popped. This is what it looks like. Notice that the sky is black. You can see the curvature of the earth. If you didn't know any better, you just think you're in space. But this is how little air is actually in the stratosphere. By the time you get up there, the sky is black from lack of air. Remember this guy? A few years ago, he jumped out of a balloon to set a world record, and he decided to jump out over New Mexico. And when he jumped out, he was at 128,000 feet, which is kind of roughly right in the middle of the stratosphere. And again, in these pictures, it looks like he's in space, right? Black sky, you can see the curvature of the earth. Looks like he's wearing a spacesuit. So even though when you look in a textbook, they will show that the atmosphere has many layers. Here's the troposphere, here's the stratosphere, and then above that something called the mesosphere, and above that something called the thermosphere. It looks like the atmosphere is pretty thick, but by the time you get up to here where those pictures were taken, it's already so little air that the sky is black. And like we said, 75% of the air is in this troposphere region. So the atmosphere is not as thick as diagrams like this imply. Most of these layers have very, very little air in them. So this brings up another point that we haven't really talked about yet, but in a cumulonimbus, we've said that you can have an anvil, and the anvil itself is made of ice, but we haven't really talked about why it is that the anvil grows in the first place. Like, why is it flat on top? Why doesn't it just keep going up? So here's another anvil from space. So the convection's happening here, and then something's causing it to flatten out. We said that this is all ice, but why is it so flat? Well, the reason it's flat is because the cumulonimbus column is coming up against the tropopause. So warm air can convect easily in the troposphere most of the time because it's getting colder with height. So warm air can rise through air that's getting colder. But up in the stratosphere, we have something called a temperature inversion. What that means is it's getting warmer with height. It's inverted to what you expect. You expect the atmosphere normally gets colder with height. The temperature inversion means it's getting warmer with height. Well, you can't make warm air rise through air that's getting warmer. So anything that's convecting, anything that's rising from the surface gets stuck right here at the tropopause. And for a cumulonimbus, that means that's the top. So if the conditions are right and we have unstable air, air will convect and it will rise, but when it gets to the tropopause, it will get stuck and it will spread out right at the tropopause, right underneath the stratosphere. So the stratosphere really acts like a cap. It prevents convection from going any further up. Now sometimes, if the conditions are right, you can get temperature inversions in other places than the stratosphere. So right here, Here's a tiny little temperature inversion. Here's a little temperature inversion. Here's a little temperature inversion. And if I'm sending up a little plume of warm air, it's going to get stuck right there. Okay? So this is critical for air pollution. So in other words, let's imagine that we're going to make another graph like these. And our graph looks like this. So the weather balloon goes up and it recognizes this kind of pattern. So it recognizes the fact that it got colder with height, and then it got warmer a little bit, and then it got colder with height, and then right here, that's our stratosphere up here, right? But this right here, this thing right here is a temperature inversion. So let's imagine that we have a city down here, and there's smoke coming out of everybody's chimney. When the smoke will rise because it's warm, but once it hits that inversion, it's going to get stuck. And if I have a whole city and a whole bunch of houses and a whole bunch of cars, all the pollution is trapped below this temperature inversion. And as long as this temperature inversion stays there, this pollution continues to be trapped below it. So sometimes you can see something like this, where you have, here's rising warm air, it's a fire, and then it hits a temperature inversion, and bam, the smoke doesn't go above that line. Here is a really severe temperature inversion where it goes right down to the surface. So any pollution that's coming out of anything, a car, a house, anything, is stuck right there along the surface of the ground. So what would cause this? Well, one of the things that causes inversions close to the surface is high pressure. So before, what we talked about is that so this is a slide from a previous lecture, and we said you have winds aloft that converge, and then they go down, and all these things happen, right? Well, the other thing that we could add to this list from last time is that we can make temperature inversions. If you make temperature inversions, you can trap pollution down here. If you trap pollution down here, you might have very poor air quality. Now, one day of this, no big deal, but you can have high pressure centers that might be parked over an area for a week or maybe 2 weeks or even more, and that starts to make the air quality really poor. On the other hand, if you have a low pressure, it actually cleans the air out. So it's like this giant vacuum cleaner in the sky, and it lifts up all the air pollution and takes it away. So let me show you a couple of pictures that show the effect of one of these temperature inversions. So here I am about 30 miles west of Albuquerque and about 10,000 feet above the ground. And I want you to notice what you can see. In other words, notice the detail, the terrain that you can see in here or in this one, right? Now, a high pressure had started building a couple days before I took these pictures, and you can see some haze in the distance. But then I went back about 2 weeks later, and that high pressure had just stayed there for 2 weeks. And when I went back and I flew to the same spot at the same height, and I took another picture in the same spot. And notice how it looks now. You can barely tell the surface is down there, right? So definitely you can't see the detail you saw before. What we're looking at is air pollution that's stuck below an inversion. And you can see from the city, this is downtown, you can see that air pollution down here below, trapped below the inversion. So sometimes the inversions can be really striking. So here's one in Kazakhstan, and you can see right at the top of the inversion and the super polluted air that's below and the really clean air that's above. So right there, that's the top of the inversion there. Now, when you have a city in a valley, you can get inversions and in other ways than the ways that I've just described. What happens is cold air can settle in the bottom of a valley, and because it's dense, it stays down there, and it forms an inversion that can last for weeks and weeks. And more locally, Salt Lake City has this problem a lot. So down there in that haze is Salt Lake City. It sits in this bowl and fills with cold air, and they will have weeks of weather just like this. So here's another image. Salt Lake City, you can see the brown above it. So there's that inversion. The top of the inversion is about right there, and you see that the tops of the mountains look a lot cleaner up here. That's cleaner air. So this happens a lot in Salt Lake City. Like weeks and weeks they'll have this kind of air pollution problems. So if you go back to the last lecture and look at those pressure maps, here's the first one we looked at, and we said that this is a big ridge of high pressure. Not only do we now know that this is sinking air and that we have cloudless skies, but if this sits over the western U.S. for days or a couple weeks, we also now know that it's going to contribute to poor air quality. That is to say that the sinking air is probably creating a temperature inversion in here, and because of that, these guys may be sitting in pretty poor air quality. There's a lot of air pollution. So we're going to go through some of the common air pollutants, and the first one is something called particulate matter, which we just abbreviate as PM. And particulate matter are physical chunks of things in the atmosphere, so you can see this stuff. So what you think of as smoke or dust, that haze in the background, that's PM. And we break PM up into two groups based on the size. And this number 2.5 and 10 refers to how many microns in diameter, and a micron is a millionth of a meter. And so all we need to know in this class is that they're both microscopic, but there's one group that's even tinier than the other group. So it could be things like pollen grains or salt grains or dust grains or bacteria or mold spores. All kinds of things could count as PM. And a naturally occurring one is that of pollen. And so pollen grains, every species of plant has a slightly different pollen grain. And if you have allergies, then you are allergic to actually the size of the particle, it turns out. So for example, the plants that I'm allergic to have a certain size, and they may not be the plants that you're allergic to because you're allergic to a different size. So that's why people are allergic to different things. It all comes down to the diameter of the pollen. Now, dust itself can be made of a lot of things, and it depends on if you've got inside dust or outside dust. And so an interesting experiment was conducted one time. There was a museum in Germany, and I don't know what they had, but it was something very valuable, and they didn't want it to get dusty. And so they had like double doors, and you had to change your clothes and all this stuff. And they found out they kept getting dust on the exhibits. So they analyzed it on the microscope, and they found out that most of the dust was actually dead skin. And it turns out we're all shedding skin all the time. And if you have a concealed indoor environment, and you go up to something and you do this on the windsill and you got dust on your finger, that's most likely dead skin. And that also means that you're constantly breathing in little particles of dead skin from other people because they're floating around in the air. Now that might gross you out, but your body absorbs those skin flakes and it doesn't hurt you. That's better for you than outside dust, because outside dust is usually little fragments of rock, and those rock fragments are usually not soluble in your body. So what happens is you breathe them in and they go into your lungs and they stay there forever. Now, here's something called silicate dust. So silicate is it's a group of minerals, rocks and minerals. And when we have dust, like in New Mexico, the dust storms, the haboobs and all that, what you're seeing mostly is silicate dust. And silicate dust has sharp edges. So this is bad because you breathe this in, it goes into your lungs, it never leaves, it wedges itself into your lungs, and every time you breathe, it wiggles a little bit. And every time it wiggles, it makes scar tissue. And eventually that can lead to lung cancer. This is the same reason that smokers get lung cancer. Okay, same kind of idea. Now, you have in your lungs, no matter where you live, you also have these little tiny microscopic spheres that are mostly carbon that come from exhaust. A lot of it comes from diesel engines, especially the older ones, but we all have them. And if you were to cut a lung open and look at it, you would see these tiny little black spheres. Now, they're not black in this image because this is a scanning electron microscope, so they look white. But if you could see them, they're little spheres of mostly carbon, surrounded by some sulfur, surrounded by some other metals. And they're floating around in the atmosphere and in the air in all cities. So we all have them. And when they do autopsies of people who live in cities, their lungs are dirty looking because we breathe so much of this exhaust. If patients go into the hospital and they're on a purifier, purified air for a couple years, their lungs will turn pink. So one type of PM that has a long and sordid history is that of asbestos. Asbestos is a naturally forming mineral. This is what it looks like when it comes out of the ground. And it looks kind of fuzzy here. You can peel it into little fibers. So if you did so, it would kind of look like this. And those fibers have some really unique properties in that, for one thing, they're fireproof, and you can sew them into different products. And so starting in the 1800s, they started to sew asbestos into fireproof cloth or fireproof blankets. And then eventually they started putting it into your house. So they started using it as insulation in your attic, fireproof, and in your walls, fireproof, and all kinds of different products. Now, today, there's asbestos in your house, but it's embedded in products. It's not freely just out in your attic like it used to be. And the reason for that is because asbestos is very hazardous to breathe. And so under a microscope, this is a scanning electron microscope, asbestos is a bunch of tiny little needles. And when you breathe them in, these are microscopic, you can't even see them. You breathe them in, they go into your lungs, they puncture your lung, and they embed themselves in there, and they never leave. So your body cannot dissolve them. And so over time, what happens is as you breathe in and out, the little fibers wiggle and create scar tissue. And that's what's shown here in the red. And eventually this will lead to lung cancer and some other lung-related diseases that are due to breathing in asbestos fibers. So we have a story in this country about a town in Montana, Libby, Montana, that was formed for the purpose of mining asbestos. And asbestos was mined in great volumes out of Libby. We don't really have any pictures, not great pictures of the mine back in the day, but this is sort of the modern equivalent. This is a asbestos mine in Canada. There's big trucks down there for scale, so it's what we call a big pit mine. So they had something similar to this in Montana, and back then they didn't think it was dangerous, and so all of this asbestos dust would go up in the air every single day and coat the entire town. So here's a picture from the 50s, and this white material you see is asbestos dust. The workers would come home, they have asbestos on their clothes, and they brush it off, and it's all in the house, and everybody's breathing it. And as a result, hundreds of people just in that town died from asbestos-related lung disease. And so there's a whole bunch of books that have been written. This is just one of them that's recently been published that detail this whole asbestos problem from Libby, Montana. Thousands of people have serious chronic health problems because of this. They think as many as 50 million U.S. homes have products from Libby, Montana in them. So it would take a long time to go over the entire history of everything that's happened regarding asbestos, but I'm going to hit a few of the high points here because the story of asbestos gets repeated for other things in our country later on. So early 1800s, we get the first U.S. patent for asbestos, and a company by the name of Johns Manville is formed. And Johns Manville is still around today. They make insulation for your house. And by the late 1800s, we're mining lots of asbestos in this country and making things out of it. By 1906, there's a doctor who starts to notice that anybody that works with asbestos seems to die prematurely. And he publishes a paper about this. And more studies are done. And by 1918, insurance companies recognize this is a real threat, and they're refusing to sell health insurance to people that work with asbestos. And by 1922, the U.S. Navy recognizes that it's hazardous, requires people to wear respirators. Okay, so we can establish that by the early 1900s, it's already known that asbestos is hazardous to human health, okay? But we continue to mine it in this country. And so as time goes on, there's more and more studies about workers that fall ill due to asbestos. And let's see, we get to the 1930s, some other countries start to passed laws regulating asbestos use, not in this country. In 1936, Johns Manville, that's the company that's mining this stuff, hires an independent group to do research to see, is this really hazardous material? And these independent group of scientists study it, and they come back and they say, yeah, it's really hazardous. And so the executives decide to suppress those studies so they aren't released. And then a similar incident happens a few years later where another group studies the effect of asbestos on mice, and they found that 80% of the mice that inhaled asbestos get cancer. That research also not published. Okay, so we're going to see, this is also going to be a common theme we're going to see in this class on some other topics. And let's see, we've got more studies come out. Here's one of note in 1960 that they realized that not just the people that work with asbestos, but their family members were getting sick, their children were getting sick, our residents in the town that didn't have anybody in the immediate family that even worked with asbestos were getting sick. So they realized it's a much broader problem. And finally, when we get to the early 70s, it's finally listed in this country as a hazardous air pollutant. And this is the first time in this country where they finally recognize that there's something wrong with asbestos and you shouldn't breathe it. Realize that this is coming like 60 years after the first papers were published in the medical science. So from that point forward, Congress has tried to pass more legislation to try to restrict how much asbestos one can breathe and be exposed to. And so let's see, there's a bunch of several things here. But as time goes on, there are more and more laws being passed regulating the use in the mining of asbestos. Now, in 1991, a bunch of manufacturers of asbestos got together and challenged the EPA, the Environmental Protection Agency, in court. And they got them to throw out some of the rules regarding asbestos. Okay, so the companies that are mining this stuff are fighting against these regulations. So as time goes by, though, eventually the regulations win. In 2002, we finally stopped mining asbestos in California. Now we're about 100 years past when the first studies were showing that it's a very dangerous thing to breathe. And we're going to kind of skip a bunch of these, but in 2010, there was a study that said that in a 10-year period, between 2000 and 2010, 43,464 Americans died from diseases related to the inhalation of asbestos, okay, just in that 10 years. So these are people that had been exposed like in the past, and it's finally catching up to them. By 2013, 50 countries have banned asbestos, but the U.S. is not one of them. And this reveals kind of a problem in our political system, which is that the asbestos industry has a lot of lobbyists. They put a lot of money into the political system to fight some of these regulations. And we've seen the effect of this. Finally, if we jump ahead, so as the years go by, we're mining less and less asbestos in this country per year. So the latest number I can find, 2015, about 360 tons of asbestos in the United States each year. It's not zero. But point is, this is a material that was deemed hazardous early 1900s, and over 100 years later, there are still people being exposed to it. And a big reason for that is lobbyist money. Big money gets into the government. You can affect politicians' votes and keep things legal that are actually hazardous to health. So this isn't to say that other countries are doing a better job necessarily. So here's a modern asbestos mine in China. All that white material you see there, that's all asbestos fibers. And in fact, here's some asbestos mining in India. These guys just wear a scarf around their mouth. That's their respirator. Or like this guy, he's got a handkerchief. I have no idea how many fibers they're breathing in, but I don't know how, we don't know how long these guys are going to live, but they're currently being exposed. So as a side note, the fact that we have millions of buildings in this country with asbestos in them sparked a new industry called the asbestos abatement industry, which is that A company will go into a building, usually it's a private building like a school or a hospital, something like that, and they will pull all the asbestos out of all the places that it was originally put in, as insulation. And it's a very expensive process. So here what they're doing is they're pulling out the asbestos that used to be up here in these joists, and all dressed up in their bunny suits and etc. And what's in these bags are these are the asbestos fibers that they're removing. Well, one of the problems of doing this is that once the asbestos is in the building and behind the walls and nobody's messing with it, it's really not that bad. But when you go in and you start digging it out, you raise all kinds of asbestos fibers again. And it's been shown that asbestos abatement probably just makes the problem worse. It's not really necessary, and the act of going in there and doing that raises a lot of asbestos dust. So some people have argued that this is totally unnecessary. But now this is an industry that has a lot of money behind it, and it keeps on going. So we're going to look at PM on earth.middleschool.net, and the way I do that is I click the word earth, and I click on particulates. And this is going to show me a lot of the PM that's in the air today. And I can look around and I can see that there's some swirls of particulate matter across the United States. I can look around the world, and there's a bunch usually in China, which we're kind of seeing here. They've got a lot of smoke. But notice what's happening over here. And so this is Africa, and in the northern part of Africa, there's this huge plume of PM. I don't know if you can notice this, but the wind, well, you can't see it so much today, but the wind is blowing it off the continent and it's headed across the ocean. You also see it over here in the Middle East. So normally, on a normal day, the most PM you will see on Earth is here in northern Africa and the Middle East. Now, why is that? So this is actually naturally occurring for the most part. North Africa is very dry, and so this is the Sahara Desert, and wind blows dust off the continent into these big plumes that go across the ocean. So these winds are called the easterlies. They're bringing dust across the ocean, and it will actually land over here in South America. Now this is important because South America, right here, this is the Amazon rainforest, right? And so one of the problems with rainforests is because they rain so much, there's almost no soil. The soil dissolves away from all the rain, and it's really hard to maintain soil, which you need to maintain a rainforest, in a place where it rains a lot. Well, here what's happening is very slowly over time, dust is blown off the continent from Africa. It travels all the way across the ocean, and it falls out over South America and very slowly adds to the floor of the rainforest. So in a way, the dust from Africa is fertilizing the rainforests of South America. So that's PM. Now we can also break it down further, and we can look at, say, PM 2.5, and we can see a few more details. You can see particulates coming from different sources. Some of these are fires. Some of these are cities with just a lot of smoke. That's probably Mexico City right there. If you go to, say, South America, we see these spots. Those are probably all fires. In Central Africa, so there's the Sahara dust, but we see a lot of dust from fires, from slash and burn practices that we'll talk about more in a second. And look at India and look at China. A lot of air pollution in the particulates here. And most of that is just industrial, people burning things. That's what most of that is. So the next pollutant on our list is VOCs, which stands for volatile organic compound. Now, volatile in this case means it evaporates fairly easily. Organic doesn't mean it comes from whole foods. It means that it's made of carbon, and that's just a different use of the word organic. Compound, it has several atoms in it. Now, it turns out that our nose and brain are set up that we can smell most VOCs. Here's an example, acetone. So acetone, this is what the chemical structure looks like. There's your carbon, so that's why it's called organic. And ladies, you know this as fingernail polish remover. You know when as soon as you remove the lid, super stinky, right? That's a VOC. Things like gasoline, paint, those are all VOCs, and usually you can smell them quite easily. Now, most of the VOCs that we have in the air here in New Mexico come from the gas and oil fields. So a lot of times what happens is that where oil forms, it rises to these natural pockets in the crust. So this is called an anticline. Now the gas will often accumulate at the top of the pocket, and the oil is a little bit below that. So if they're drilling, they might be drilling to get the gas on purpose, and sometimes when that happens, some of it gets out and gets into the atmosphere. Sometimes they're after the oil, and the gases are just kind of in the way. Either way, a lot of times the gas leaks out and gets into the atmosphere. So here's a pump jack. So its job is to pump petroleum, which is a liquid. But if you've been by one of these, there's an odor in the air. And a lot of what you're smelling are VOCs. There's natural gas coming out of this well, a little bit. Here's a natural gas well. So they've dug a hole and they basically just put in a valve, and natural gas comes out of this pipe, and then it goes on to a processing plant. But there's also natural gas kind of seeping out of the ground around where this well was built. Now, once natural gas comes out of the ground, they can't just directly sell it to you for your gas stove. It's got to go through a few steps. It's got to be purified and clean, separated out into different components sometimes, and then they got to compress it and they push it down a pipe. So maybe there's a gas, one of these over by Carlsbad, and then the way it gets to Albuquerque is there's an underground pipe that takes it all the way from Carlsbad to Albuquerque. And so a gas plant is kind of the first stage in that, where they separate out the different components and purify it. And then in order to get it all the way to Albuquerque down the pipe, they've got to compress it in several different places along the way, and those are called gas compressor stations. And each one of these, a little bit is lost in the atmosphere, and in the gas plants and the gas compressor stations. And then a lot of times, again, if they're after oil and they don't want the gas, they still have to do something with it. So a lot of times they'll just burn it. That's called flaring. So what's happening here is they're trying to get petroleum, but they also got some gas that came out with it, but it's not worth the effort and the money to try to, compress it and clean it and all that. So they just rather burn it. So that also emits some VOCs into the atmosphere. Also, some PM. There's a lot of PM in these black clouds here. Then another source of VOC is the refinery. So refineries are where we take petroleum and we basically put it under vessels of pressure and heat, and we separate out raw petroleum oil, crude oil, into the different components. So gasoline, diesel, kerosene, all those things come from crude petroleum, but they have to be processed in a refinery to make those products. And so in that process, a lot of VOCs are emitted to the atmosphere. And in New Mexico, we have a couple refineries. One you may have been exposed to is in Artesia. If you've ever been through the town of Artesia, it has a particular odor. And what you're smelling are VOCs, and they're coming from this refinery. So the Navajo refinery is the official name of this. And it's right in the middle of town. You drive right by it, and you can smell it. Those are VOCs. Moving on to our next pollutant is sulfur dioxide. And sulfur is in a lot of fossil fuels. So when you burn fossil fuels, SO2 is a common byproduct. You burn coal, you burn gasoline, you burn diesel, you produce sulfur. Now, one of the problems is that sulfur by itself isn't quite that harmful, but once it gets into the atmosphere, it'll combine with water molecules and form sulfuric acid. That sulfuric acid that's floating around in the atmosphere then condenses to form rain, and you get acidic rain. So here is some clouds that are forming. Here's a plume of sulfur dioxide that's actually forming clouds that are acidic. So we know that cumulus clouds don't rain, but if they were to produce rain, you get very acidic rain coming out of these clouds. Now, acid rain used to be a really big deal, and today our big environmental problem is global warming. In the 80s, it was the ozone hole. You go back 100 years, it was acid rain. Acid rain stresses vegetation. So the branch on the left has been exposed to acidic rain, and you can see it's not doing so well. In fact, when in the late 1800s, people started burning lots of coal in steam engines, and then eventually people started to produce electricity. There was a lot of coal being burned and producing a lot of sulfur. It went out into the atmosphere, made a lot of acid rain, and there are entire swaths of forest in Europe that were killed because of acid rain. And you can still see them today. They're starting to come back, but there are places where there's just millions of acres of dead trees from acid rain. And most of this occurred in the late 1800s, early 1900s. Another thing that happens is that acid rain reacts with limestone and marble and dissolves it. So here's a marble statue that was carved in 1702, and 1908, this is what it looks like. So it's been around 200 years at this point. 1968, notice that it looks like someone just took an eraser to it, and acid rain basically dissolved away this statue. And we've lost a lot of statues worldwide to acidic rain. Here's another example. This is something called an obelisk. It's made out of limestone, and it's from Egypt. And it was carved out of limestone about 3,000 years ago. And you can see the hieroglyphics in this old picture. This is what it looked like in 1884. There was a point in history where it was okay for cities to just go to Egypt and take things. And so New York City just decided, hey, that would be cool to have that in Central Park. So they took it and they put it in Central Park. And you'll notice that a lot of the hieroglyphics are not recognizable anymore. In fact, this is what it looks like up close. It has this kind of pockmarked texture. Acid rain dissolved away a lot of the hieroglyphics in that 3,000-year-old obelisk. And it just happened within 100 years. So we're going to return now to earth.nullschool.net, and we're going to look for sulfur. So I click the word earth, and under mode, I'm going to chem, and then under overlay to SO2. Okay, so now the colors represent sulfur dioxide emissions. And if I zoom in here across the US, I can see a whole bunch of little red dots with tails. Every one of those is a coal-fired power plant, including some here in New Mexico. So coal has sulfur in it, and in this country, coal-fired power plants are required to remove at least some of the sulfur out of the exhaust, but some of it still gets into the atmosphere, and that's what all these red dots are. So in the eastern part of the country, there's a whole lot more coal-fired power plants than there are in the west, so we see a lot more sulfur emissions out there. But let's look around the world here. Not much happening in Africa. But, oh boy, look at China. So China has a lot of coal-fired power plants, and they don't have the emission regulations that we do. So they emit a lot more sulfur than we do. And you can see on here, there's just a bright purple blob. India's got a fair amount too, right? But China really has most of the sulfur emissions right now. Also, you might notice, let's see if we can find it. Here's some. See these stripes? Like that stripe right there that goes across the ocean. Here's another one. That stripe. Do you know why there might be stripes of sulfur out in the ocean? So those stripes of sulfur dioxide that are out in the ocean, those are shipping lanes. And out in the ocean, there are these giant container ships. Just about anything you've ever bought has been on a container ship at some point in its life. And these things are out in the ocean. They're enormous. They have giant engines, and they burn really cheap fuel that has a lot of sulfur in it. And the reason they can get away with this is because out in the open ocean, there's no pollution laws. When you're 200 nautical miles from the shoreline, then the country in question, their air pollution laws apply. But out in the rest of the ocean, there's no laws. And so these big container ships really pollute. And put it in perspective, 15 of these big container ships produce as much SO2 as all of the cars in the world combined, okay? And then figure, well, there's 6,000 of those giant container ships out in the ocean right now, and 85,000 commercial ships that are currently in use. So there's a lot of air pollution out in the ocean from these giant ships. Next one on our list is oxides of nitrogen, which we abbreviate as NOx. NOx are two different molecules, NO and NO2. You get them when you burn fuel at high temperatures. So for example, a car engine burns gasoline at a pretty high temperature, it produces NOx. And if you live in an area where you have to get your car emissions tested, NOx is one of the things that they're testing for. Well, one of the problems with NOx is that it combines with atmospheric water vapor to produce an acid in a similar way that sulfur does, except instead of sulfuric acid, it produces something called nitric acid. And this also contributes to acid rain. Ozone. So, we've talked about ozone in the stratosphere, and we say this is wonderful, marvelous thing that protects us down here from UV. Gotta have it. However, there's a second source of ozone that's not natural. It's down here at the surface. And it's really, really bad for you. Pure oxygen, O2, is an oxidizing compound. O3 is an especially oxidizing compound. If you breathe in O3, it attacks all the tissues in your body. And it's a major lung irritant. And the way you get ozone at the surface is if you have VOCs plus NOx in the presence of sunlight, those three things will react to produce ozone. So some big cities, especially those that have temperature inversions like we've been talking about, they'll issue ozone warnings and basically don't go outside because the ozone is so bad. Now in Albuquerque, we don't really have that problem here. We don't have enough air pollution that ozone really ever becomes an issue. But in some cities, every day there's some sort of ozone reading or ozone warning that gets communicated to the public. Carbon monoxide, next on our list. Carbon monoxide is sometimes often confused with CO2. Okay, CO versus CO2, two different things. Carbon monoxide, like almost everything we've been talking about here, is a product of burning fuel. So carbon monoxide, you can't see it, you can't smell it, but it's poisonous. And what happens is, normally, when you breathe in oxygen, oxygen goes into your bloodstream, it finds a red blood cell, it attaches to a certain place in the red blood cell, there's some electrons exchanged, and then it leaves as a carbon dioxide, okay? Carbon monoxide comes in, finds that spot on your red blood cell, attaches itself, and stays there. And so that red blood cell no longer can operate as a red blood cell. And so as you breathe in carbon monoxide, what happens is all the receptors in your red blood cells become choked with these carbon monoxide molecules. Now, your experience is you start to get sleepy, right? So what's happening is you're slowly becoming suffocated. And eventually you say, oh, I'm so sleepy, I'll take a nap, and then you never wake up. That's carbon monoxide poisoning. So people that commit suicide by breathing car exhaust in the garage, what's actually killing them is the carbon monoxide. Okay, it's coming out of all car exhaust. So we're going to go to earth.newellschool.net and look at some carbon monoxide. So mode is still chem. Overlay I'm changing to CO. And now the bright spots are plumes of carbon monoxide. And it looks like here we maybe got some fires. That's probably just automobile exhaust from New York City, automobile exhaust from LA, Chicago. Let's look down here. Okay. So here we are in South America, and there's this cluster of these plumes of carbon monoxide, every one of those dots. And these are fires. And these are fires started by humans, because what we're looking at is what we call slash and burn agriculture. So Americans like hamburgers. Hamburgers come from cows. And if you want to grow cows in another country, you can't do it in rainforests. So cows like grass. So what they do is they chop down the rainforest and they burn it. And then they grow grass. But as we said a few minutes ago, there's not much soil in the rainforest. So grass doesn't last very long. So you get a couple seasons of grass out of it, and then the cows need to move on. So you got to chop more rainforest down and repeat the process. So this is all agriculture practices here, mostly to grow cattle to sell to us. In fact, if we look over here in Africa, okay, we got some more over here. So each one of these little spots is a place where there's it's a fire due to slash and burn for the most part. So let's see here. There's India. Oh, China. You never fail to disappoint. So a lot of carbon monoxide emissions from China today. So again, that's, mostly, it's all from burning fuel. So whether that's coal-fired power plants or automobiles or factories or something, that's what's causing it. So it looks like today the world record holder for CO emissions is China once again. So next up on our list of air pollutants are the heavy metals lead, which is pretty soft, and mercury, which is liquid at room temperature. It may not make sense that you could have heavy metals in the air, but there's a couple ways it could happen. With lead, it used to be that lead was in gasoline, and they put it in gasoline because it was a cheap way of raising the octane level. And so for 75 years or so, we burned lead gasoline in our cars, and all that lead went out into the atmosphere. So much so that there's really almost no place you can go on Earth now and not find lead in the soil. So in the 80s, we started to phase out leaded gasoline. So for a while, you could buy regular gas, which meant it had lead in it, and then the unleaded. And then about a decade after that, they got rid of the leaded gasoline altogether, and your only choice now is unleaded, at least for cars in this country. Lead also was in all paint. It forms compounds that are very colorful, so they used to use lead to make the pigment. And so what would happen is they would paint a house with lead-based paint, and then the paint would chip off over time and flutter away into the wind, and you could get lead into the atmosphere that way. So in the recent year or so, Flint, Michigan has been in the news about the lead in their water. But there's actually a lot of places that have lead problems. And this map you can explore if you want, and you can find where you live, and it'll tell you how much lead is in the environment. If you zoom in on Albuquerque, you see there's a lot of red zones here around Albuquerque. And these are neighborhoods, most of these are neighborhoods that were built with lead-based paint, including the house that this is being recorded in. So this is lead all over the environment. It's in the water, in the paint, in the soil, whatever. Right now we're talking about lead as an air pollutant only. Now mercury can also get into the air because it's naturally occurring in coal. So here's a coal-fired power plant. There's a big pile of coal there they're going to burn. And in an earlier lecture we talked about how water vapor condenses out to make a little cloud. That's from burning hydrocarbons in the coal. But what's also coming out of the chimney is mercury. And so every coal-fired power plant is putting a little bit of mercury into the atmosphere. Now, mercury ends up in the ecosystem and can get concentrated in certain organisms like fish. So somehow or another, the biology of fish is such that mercury gets concentrated in fish tissues. And there's places where the fish have so much mercury that you can't eat the fish. So mercury is a neurotoxin. It causes brain cancer, among other things. And so if you eat fish, it's wise to pick fish that don't eat other fish. Okay, so for example, big fish that are predators that eat other fish, they end up with more mercury in their bodies. It gets concentrated in their bodies. Your healthier fish are the ones that don't eat other fish, but maybe eat insects or something like that. So your salmon, steelhead, etc. Those are healthier fish. This is especially true if you're pregnant. So if you think you're pregnant, don't eat tuna, okay? Because tuna has measurable amounts of mercury in it. So a lot of people may not realize this, but a lot of the big American cities went through a period of time where the air pollution got so bad that they were almost uninhabitable. And these pictures are from the 40s, 50s, and 60s of some cities like Los Angeles and San Francisco, New York. And what looks like fog is actually air pollution. And it became really unpleasant to live there. You know, everybody's eyes are burning. You couldn't see the buildings. It was really not pleasant to be outside. And so finally, Congress decides to do something about it starting in the 50s. And it starts out with something called the Air Pollution Control Act. And it really didn't do much by today's standards. It gave the Surgeon General permission to distribute information about air pollution, like that's a big nothing, but baby steps, okay? And then 1963, they establish something called the Clean Air Act. And this is going to, at first, doesn't have any teeth really, but it's going to grow in later years. And at first, all it does is it establishes a federal program to study air pollution. But so far, people can still pollute as much as they want. In fact, here's a picture from 1970. This is a battery processing plant. Big plumes of black acrid smoke going out in the atmosphere, completely legal. There's no laws regarding air pollution at that point. Now, in the 1960s, there's going to be some laws that start to come into effect regarding air pollution with cars. So the first amendment to the Clean Air Act occurs in 1965, called the Motor Vehicle Air Pollution Control Act. And what it said is that cars that are going to start being built in 1968 have to be cleaner than the previous models. That, compared to a 1963 car, have to emit 72% less VOCs and 56% less carbon monoxide. Okay, so that's the very first time there's a law regarding air pollution with cars. So prior to 1968, cars could pollute as much as they wanted. There was no laws regarding that. Well, a lot of things are happening in the late 60s, early 70s regarding air pollution. In fact, regarding pollution in general, there was this sort of environmental movement afoot, and people were protesting about the quality, the poor quality of the air. So here's some photos from those times. And there's a bunch of little laws that are kind of being passed. But in 1970, they established the Environmental Protection Agency. So this is an agency that's designed to be in charge of all these environmental problems. Okay, so prior to 1970, there were a bunch of little laws, some regarding air, some with water, some with wildlife, and they were taken up by different agencies, and the EPA was supposed to head all of those things, okay, consolidate all those different laws. So that happens in 1970. Then the same year, there were amendments to that Clean Air Act, the one that they started in 1963. And this is where they introduced the list of pollutants that we've been talking about, PM, VOCs, SO2. These are things that now can be regulated for the first time ever, all right? And this law becomes amended in the future. So there's amendments in 1977, there's amendments in 1990, and what happens throughout time is that more and more air pollutants are added to the list. So we went over some of the big ones, right? SO2, carbon monoxide, those things. As time has gone on, more pollutants have been added to the list and more regulations about how much you're allowed to emit into the atmosphere. Well, as a result of this, so here's a graph, starts in 1980, goes to the year 2013, and it's got a bunch of things on here. But this green line is the big pollutants that we've talked about, okay? VOCs, PM, all those things. They've gone down since 1980 to 2013 by 62%. So there's 62% less of those emissions going into the air compared to 1980. During that same time, we have more people, we have more cars, we're traveling more miles, we're using more electricity. So even though there's more of us driving more, owning more cars, the amount of actual air pollution has been going down. And this is because of the Clean Air Act. Another way you can measure this are in the amount of smoggy days. So this is in the Bay Area, so near San Francisco, and they were keeping track of how many days of really hazardous smog that they had. So this is 1969, and you can see they've got, somewhat looks like about 65 days of really extreme smog. And over time, there's good years and bad years, but they start to hit days with 0 days of really intense smog. And again, this is due to the Clean Air Act. There's more people there today, there's more cars there today, but their air has actually been getting cleaner. And you can see photographs of this. This is LA 1968 versus LA 2005, right? So the Clean Air Act and these rules actually had a big impact. Cars have been getting cleaner and cleaner every year. So every couple of years, manufacturers have been required to produce automobiles that pollute less and less. You may not know this, but there are machines that will be set up on the side of the road that will measure the pollution of your car. We don't really use them so much in New Mexico, but they do this in California, and this is data from Phoenix. So what they're looking for is, so a car drives by, and it's measuring the pollution of the car that just drove by, right? That's what it's measuring. So it's measuring VOC and NOx. And there's 3 different kinds of cars here: SUVs, pickups, small cars, small pickups, and then just cars. And what you notice from 1981 to 1999, that the amount of VOCs are going down and the amount of NOx going down, okay? And so that, again, that's due to regulation from the Clean Air Act. Manufacturers are required to meet these certain standards for air pollution. So, without making things political, we have to talk about making things political, because we're in a very weird time. And I don't know when you're going to watch this, but I'm recording this in early 2008, and we've had the Trump administration now for a year, and things are changing. Things are chaotic. So without diving too deep into it, let's talk about a couple things. If you took this class 10 years ago, we would talk about the Clean Air Act, we talk about the rules. Every year things are getting better. Every year the air is getting cleaner, right? But now everything's in flux. And so one of the things that's happened is Trump has appointed Scott Pruitt in charge of the EPA. Well, Scott Pruitt has nothing to do with the environment. In fact, his background is that he was a lawyer who was suing the EPA prior to this on behalf of oil and gas companies. So his big thing is he would like the EPA to go away. He was suing kind of like to get rid of these air pollution laws, and now he's in charge of it, right? This is a classic political move. If your political party doesn't like a certain agency, you take someone else that hates that agency and you put them in charge of it. Okay, so this is not new. Okay, this kind of thing has been going on a long time. But one of the things this brings up is, well, okay, so what's going to happen to all these air pollution laws, right? And the answer is we're not totally sure. But about a year ago, Trump signs an executive order to, quote unquote, initiate a review of the air pollution policies. And they have been promising, the Trump administration in general has been promising that they're going to remove a lot of these air pollution regulations. Now, as of right now, nothing really concrete has been done. They've rolled back a few things for coal-fired power plants, but they really haven't completely got rid of the laws that we've been talking about for the Clean Air Act. But we're 1 year in, so I have no idea what's going to happen. I don't want to dwell on this too much, except to say times are changing. And it's a little ironic that I just showed you pictures of this from the 1960s, and now I can show you the same pictures of this from 2017. So people protesting about the exact same thing 40 years later. Well, one of the things that came out of the Clean Air Act is something called the AQI. And the AQI is the Air Quality Index. And what it does is it establishes a monitoring system for air. And so we have a machine that collects air, it measures the air pollution, and then it rates it. It's numerical from 0 to 500. And if you're in the 0 to 50 zone, that's considered good. That's where you want your air most of the time. 50 to 100, moderate, and so on and so forth, all the way to hazardous, which is 300 to 500. And they assign a color to this as well. Well, you can go online and you can check the air quality all across the country. And here's this website right here. And we're going to go to this right now. So here's what this website looks like, and we can visually just kind of look at the quality of the air. So we see a lot of green and yellow. That's good news. And you can zoom in and click on any station to get a reading. So if I click on this one, Santa Fe Airport. Okay, so it's reporting 34. That's good, right? That's pretty clean air. And by and large, we're doing pretty well. I don't know what's going on here. We've got some near the border of 500. That's bad. If we go down to Mexico, looks like we've got some pretty polluted air down here by Mexico City. That's not too surprising. And let's go across the world here. So over Europe here, looks like we got a batch of pretty bad air right in there. Might be related to a temperature inversion. I'm not really sure. Let's keep going. And oh, China. That does not look good. So we got a lot of red, and we have a lot of dark red. And in fact, if you look at these, if you can read it, it says 999. That means the pollution is so bad it's clear off the scale. So when they invented the AQI scale, it only went from 0 to 500. And there are air pollution monitors in China that routinely report air pollution over 1,000. And in fact, the government isn't completely forthcoming with how bad the air quality there is. But we have an embassy in China, and we have an air monitor on the roof. And so we actually know how bad it is. And it's routinely like 1,500 on the AQI scale, something like that. So, in fact, China is a pretty interesting study in what happens if you don't have any air quality regulations. So, this is called a sunny day in China, and this is not fog, this is air pollution. And this is the kind of air, when you have an AQI of 999, this is what it looks like, okay? And it comes in like a fog, and it's often this way for weeks at a time in Beijing. And people walk around with dust masks on. Sometimes people exercise outside with dust masks on. Other times students exercise inside. Look at these guys going on the marathon with their respirators on. These guys are pretty gangster. They don't care. They're going to breathe it in anyway. This is what a satellite picture of China often looks like. All this brown that you see, that's all air pollution. So it's worth pointing out that one of the reasons the air pollution is so bad in China is that, unlike us, they don't have or have not historically had any laws regarding air pollution. They've also been growing. They've been putting up like several coal-fired power plants per week in the last several years. But unlike here, where we have a lot of fairly strict regulations regarding air pollution, they've just pretty much let people do whatever they want. And so you can kind of see the result of that system here. In fact, in 2015, they were going to have a parade to celebrate the end of World War II. So for a couple weeks leading up to the parade, they took cars off the streets, they shut down power plants, they shut down factories. And the day of the parade, or the day before the parade, I guess it is, this is what it looked like. This is what Beijing looked like. You can actually see the sky. Literally the day after the parade, they are like, all right, back to work, everybody. This is what it looked like, okay? So they could have clean air. It's possible, but they're going to have to invest, time, energy, and political will to clean up their air, to keep it, kind of like what we have here. So, to summarize, the atmosphere is subdivided into layers, with the lowest two layers being the troposphere, and above that the stratosphere. And the stratosphere has a big temperature inversion, and that's what blocks convection. Now, high pressure centers can create temperature inversions lower down in the troposphere. And if you have one, it will prevent things from convecting and going up into the atmosphere, and that is what traps air pollution. So we went through the different pollutants, and we talked about how legally nothing really happened in this country till the 1970s, and then we started passing laws regarding air pollution. And the only things that are pollutant are things that are actually dangerous to us. So as we'll talk about in a future lecture, greenhouse gases are not part of this list. That's a separate thing. And up until a year ago, with the new administration, the story has been that each year that goes by, air pollution here in this country gets better and better, and the restrictions become tighter and tighter. So your cars are cleaner, your factories are cleaner, etc. Right now, who knows what's going to happen? All right. Thanks for listening.